Jupiter has hurled thousands of bodies out of our solar system. That's the role we like to give it. Protector, shield, a great, silent shepherd at the edge of the inner worlds. But here's the quiet detail people skip. For every object it flings away, its gravity can angle another one inward. Right now, an interstellar passerby called 3 Atlas is racing toward the gas giant at more than 60 kilometers per second, and something unsettling is beginning to show, like a needle twitching on an instrument panel. The trajectory isn't behaving the way the clean equations promise. Small forces we don't fully pin down are nudging it during the most gravitationally intense moment imaginable. They're the footnotes of physics. But footnotes can steer futures. If those nudges line up just right, Jupiter doesn't deflect 3 Atlas away from Earth. It can point it straight at us. What if the same tiny forces we barely understand are using Jupiter's gravity like a hinge, turning this visitor around on a pivot of warped space-time? Stay until the end, because the answer decides whether this is a near miss, or the first chapter of something we cannot stop. If you're as captivated by this cosmic mystery as I am, tap like and subscribe so you stay close as new details surface. And leave a comment telling me where you're watching from, what time it is in your corner of the world, and what you think is really moving out there beyond Jupiter's orbit. Part 1. The claim nobody wants to touch. Jupiter has always been cast as our guardian. That's the story we repeat to ourselves. The solar system's largest planet, a gas giant with gravity so intense it can bend light, a world of banded clouds and endless storms sitting between us and the dark. For decades, astronomers have described Jupiter as Earth's bodyguard, a cosmic bouncer that catches or diverts comets and asteroids before they reach the inner planets. We built an entire soothing narrative around it. Jupiter shields us. Jupiter saves us. But what if that's only half the truth? What if, under the right geometry, Jupiter doesn't protect Earth at all? What if it aims? On October 7th, 2023, astronomers confirmed something extraordinary. An object designated 3 Atlas became the third verified interstellar visitor to our solar system, stamped with a path no local rock should have. Not from the Kuiper belt, not from the Oort cloud, from another star system entirely. It came screaming through the dark at velocities no native solar system object should have, carrying the riddle of whatever stellar neighborhood shaped it, whatever cold forge and distant sun let it form. By every conventional expectation, 3 Atlas should behave like its predecessors, Oumuamua and 2I Boris. It should pass through once and never return. Interstellar objects don't orbit our sun. They don't belong to our gravitational family. They're tourists, not residents. They arrive, they depart, and we never see them again. Except something odd happened as 3 Atlas closed in on Jupiter. The trajectory calculations began to shift, and the shift refused to settle. Not dramatically, not in a way that makes headlines, but enough to catch the attention of the specialists who live inside orbital mechanics. Small refinements in the predicted path, tiny adjustments to the expected exit velocity, the kind of changes that usually mean better data, better instruments, better understanding, the slow tightening of a forecast. But this time, a few of those refinements leaned in an uncomfortable direction. They hinted that 3I Atlas might not be leaving as predictably as everyone assumed. Let me be absolutely clear. No space agency has issued a statement claiming 3I Atlas is turning around. NASA hasn't called a press conference. The European Space Agency hasn't raised alarms. The official position is unchanged. This is an interstellar object on a hyperbolic trajectory, passing through, not staying. But in the margins of the data, in the quiet exchanges between researchers who study gravitational interactions, another conversation is happening. It's speculative, and it stays deliberately quiet. It lives in preprint footnotes, in late-night emails, in plots where one line won't quite sit on top of another. It's uncomfortable, and it circles a phrase you won't see in any official report. Powered slingshot. The idea sounds almost ridiculous, like science fiction trying to sneak into a spreadsheet. In spaceflight, a slingshot usually means a gravity assist. Spacecraft use them constantly. Voyager used Jupiter to accelerate toward the outer planets. Cassini used multiple planetary flybys to reach Saturn. Those maneuvers are passive. The spacecraft doesn't fire engines at closest approach. Gravity does the work. The object comes in fast, whips around the planet, and leaves even faster redirected, but not deciding anything. A powered slingshot would be different. It would blend gravitational acceleration with active thrust, using Jupiter not just as a boost, but as a pivot, a controlled bend at impossible speed, a U-turn at cosmic velocity. Why even entertain it? Because of orbital residuals, the technical name for the tiny mismatches between what the models predict and what telescopes actually see. Every calculation hides assumptions, and every assumption has a shadow. The mass of the object, its shape, its rotation, whether it's venting gas or shedding dust. Those inputs go into equations that return predicted positions, velocities, trajectories. When reality doesn't quite match, you get residuals. Usually they're small. Usually they vanish with better measurements or slightly refined assumptions. Usually they don't matter. But residuals are where surprises sleep. They're cracks in our certainty, the place the universe slips a note under the door. Every major orbital shock in history, every unexpected change, started as an unexplained residual. When Oumuamua drifted from its predicted path in 2018, scientists first waved it away as noise. Then the deviation persisted. Eventually, they accepted that something was pushing it, a force beyond gravity alone. The current consensus blames outgassing jets of sublimating material acting like tiny rocket engines. Uncomfortable, but explainable. Natural. The residuals around 3 Atlas are smaller, subtler, but they're there. And they keep showing up, stubborn as a heartbeat. Some researchers have noted that a few model assumptions, especially the object's mass distribution and rotation state, could be wrong. Not wildly wrong, just wrong enough. If the mass differs from the estimate, the Jovian interaction changes. If the rotation produces asymmetric outgassing, thrust vectors shift, and the average thrust stops averaging. If the timing of perihelion, the closest approach to Jupiter, coincides with peak activity on the surface, the effects compound. Here's the fragile assumption under every confident prediction about 3I Atlas, that we understand every force acting on it. Gravity from the Sun, gravity from Jupiter, maybe a little outgassing if it's a comet. Add them up, solve the equations, predict the path. Simple, except it's only simple if the list is complete. If there's even one force we're underestimating, one parameter we measured slightly wrong, one interaction we didn't account for, the predictions drift. And at interstellar velocities, tiny drifts accumulate into enormous changes over time, millimeters per second, becoming millions of miles of difference. So why isn't this in press releases? Why are official statements still confident that 3I Atlas is leaving forever? Because extraordinary claims require extraordinary evidence, and right now the evidence is circumstantial at best. Those residuals could mean a dozen things. The trajectory refinements could be artifacts of improving data quality. The powered maneuver idea could be exactly what it sounds like: speculation, unfounded, and irresponsible. No scientist wants to be the one who cried wolf about an interstellar object. No agency wants to spark panic over uncertainties that will probably resolve into nothing. But here's the question nobody wants to say out loud. What if the assumption that it's leaving is the mistake? What if we're so committed to the story, interstellar objects pass through and disappear, that we're missing something in plain sight? What if Jupiter's gravity, the immense protective force we celebrate, is about to do something we never modeled for? What if, instead of deflecting 3 Atlas away from Earth, Jupiter is quietly lining up the shot? Part 2. Jupiter. Shield, assassin, or neutral party. Jupiter isn't your friend. It isn't your enemy either. It's a gravitational fact, indifferent, an immense warping spacetime, with the casual authority of something that outweighs everything else in the solar system, except the Sun. Its magnetosphere crackles with radiation, but its math is calm, 417 times the mass of Earth, packed into a sphere so large you could fit over 1,300 Earths inside it. When you talk about Jupiter's gravity, you're talking about a force that shapes more than its own neighborhood. It nudges and sculpts trajectories across the inner solar system, and we've told ourselves a comforting story about what that influence means. It goes like this. Jupiter sits in the 5th orbital position, a massive gravitational sink, catching or deflecting dangerous objects before they can threaten Earth. Comets from the outer reaches, asteroids knocked loose from unstable orbits, they pass through Jupiter's sphere of influence. Some get captured, some get ejected from the solar system entirely, some get redirected into harmless paths. Earth benefits. We're told Jupiter is our cosmic bodyguard, our planetary shield. The reason we haven't been pummeled into sterility by constant deep space debris, it's a nice story. It's also incomplete, because Jupiter doesn't only deflect threats outward, sometimes it deflects them inward. Think of Comet Shoemaker Levy 9. In July 1994, astronomers watched a shattered comet slam into Jupiter with spectacular violence. 21 distinct impacts over 6 days, each releasing energies equivalent to millions of megatons of TNT. The scars stayed visible from Earth for months. And here's what most people miss. Jupiter didn't capture it from interstellar space. It didn't heroically intercept something aimed at Earth. Jupiter tore that comet apart with tidal forces, locked it into an unstable orbit, and then collided with it, like gravity closing its own trap. Jupiter created the threat, then absorbed it. The bodyguard metaphor feels less comforting when you realize the bodyguard sometimes starts the fight just to stay sharp. And then there are the Jupiter family comets, objects born in the outer solar system, gravitationally kicked around until they end up on paths that pass repeatedly through the inner planets. Jupiter didn't shield us from them. Jupiter delivered them. Every few years, a Jupiter family comet slides past Earth. Most are small, most miss, but most is not all. The perturbations that send them inward come from the same Jovian gravity. And we're supposed to feel grateful. Even though gravity doesn't have preferences, it doesn't choose to protect Earth or endanger it. Gravity is geometry mass warping spacetime. If you're a small object approaching Jupiter, what happens depends on angle, velocity, and timing. Change any of those just a little, and you get a completely different outcome. Approach from one side, and you're flung toward interstellar space. Approach from a slightly different angle, and you're redirected toward the sun. Approach at exactly the right angle, with exactly the right velocity, and you can be aimed precisely at Earth. NASA understands this. Mission planners know Jupiter's gravity is not a shield. It's a tool. A gravity assist doesn't care about intentions or origins. It cares about vectors, velocities, and the curvature of space-time around massive bodies. When Voyager 2 used Jupiter to reach Uranus and Neptune, it exploited the same physics that could redirect an asteroid toward Earth. The difference is intention and control. Voyager 2 fired its engines at precisely calculated moments to get the outcome it wanted. An uncontrolled object simply goes where the math sends it. And here's the uncomfortable part. At interstellar speeds, Jupiter's influence becomes even more dramatic. Think of it as a gravitational lens, not for light, but for trajectories, bending paths the way glass bends a beam. A fast-moving object passing through Jupiter's well experiences extreme bending of its path. The faster you're moving, the more energy you carry. And the more that energy can be redirected rather than absorbed. A slow object might be captured. A fast object gets whipped around and sent somewhere else. The question is, where? For 3 Atlas, moving at over 60 kilometers per second relative to the solar system, Jupiter is an enormous energy reservoir. If the object passes close enough on the right line, Jupiter can add or subtract velocity in almost any direction. Approach from behind Jupiter relative to its orbit, and you gain energy. Approach from ahead and you lose it. Approach at an angle, and you're redirected. The exact outcome depends on sub-degree precision in the approach, and those angles can shift based on forces we may not be measuring correctly. So is Jupiter protecting us from 3I Atlas, or aiming it? The answer is neither. Jupiter is doing what a 417 Earth mass ball of hydrogen and helium does, warping spacetime in proportion to its mass, following rules that don't bend for our comfort. If 3 Atlas passes through that warped region, its trajectory changes. Whether that change points away from Earth or toward it is purely geometry and velocity. There's no shield, there's no weapon, there's only math indifferent and precise. But we don't like indifference. We like stories. We like protection. We like imagining Jupiter standing between us and danger, a benevolent giant keeping watch. The reality is sharper. Jupiter amplifies consequences. If an object is already going to miss Earth, Jupiter can make it miss by more. If an object is already a threat, Jupiter can make that threat worse. And if an object is balanced on a knife's edge between safety and danger, Jupiter tips it one way or the other, with no regard for what we'd prefer. So the real question isn't whether Jupiter protects Earth. It's which side of the blade 3 Atlas is on right now. And who's holding the knife? Part 3. Hyperbolic. Until it isn't. Hyperbolic trajectory gets used like a synonym for unstoppable, permanent, guaranteed to leave. When an object is hyperbolic, its velocity exceeds the solar system's escape velocity. It's moving too fast to be captured. It came from somewhere else, with energy to spare. It's passing through, and it's supposed to keep going forever. The math looks clean. The conclusion feels definitive. Except the math is only as solid as the measurements you feed it. And measurements are never perfect. So let's ground hyperbolic in everyday language. Imagine throwing a ball straight up from Earth's surface. Throw it slowly, and it rises and falls back down in an ellipse. Throw it faster, and it goes higher before returning. Throw it at exactly 11.2 kilometers per second, and it never comes back. It escapes Earth's gravity. That's escape velocity. Throw it even faster, and the path becomes hyperbolic. The ball doesn't just escape, it escapes with energy left over. For 3 Atlas, that excess is enormous. It isn't barely slipping away. It's racing out with enough kinetic energy to make recapture feel impossible. The sun's gravity pulls at it, slowing it slightly, but not enough to stop it. Jupiter tugs during the flyby, changing direction, but not, in the standard model, changing its status as unbound. By every standard calculation, 3I Atlas should leave the solar system and never return. Should. But hyperbolic doesn't mean immune to change. It only means the current velocity is above the escape threshold. If that velocity drops even a little, the trajectory shifts. Not like a car slamming brakes and reversing, more like a curve that tightens by a whisper, almost too soft to notice. The arc bends a little more. The exit angle changes by fractions of a degree. The excess velocity shrinks. And in orbital mechanics, small changes create enormous downstream effects. And that's why a fraction of a degree, here, can matter more than 1,000 miles by the time it reaches our neighborhood. So how do you measure excess velocity? You track position over time, measure speed, calculate gravitational potential energy from distance to the sun, and subtract the two. What remains is excess kinetic energy, the surplus that lets it escape. If position measurements are off by even a few kilometers, the velocity changes. If your distance estimate is wrong by a tiny percentage, the potential term shifts. Stack enough small errors, and your confidence in definitely hyperbolic starts to soften. Now add non-gravitational forces. Outgassing from a comet nucleus creates thrust usually tiny, but persistent. Solar radiation pressure pushes like wind on a sail. Both can add or remove kinetic energy. If outgassing is symmetric, it barely matters. But if it's directional venting mostly from one sunlit side, the imbalance becomes a net force. Over weeks or months, that net force accumulates into a measurable velocity change. For a bound object already in a stable orbit, it might shift the period by days, or adjust perihelion slightly. Annoying, but not catastrophic. For an object on the edge of escape, it can be the difference between leaving and staying. And we don't measure these forces directly. We infer them from residuals. From the mismatch between predicted and observed positions. If the residuals are explained wrong, the inference is wrong. Here's where it gets genuinely uncomfortable. Energy loss in space doesn't look like energy loss on Earth. There's no friction, no air resistance. An object doesn't slow smoothly and stop. Instead, energy redistributes between kinetic and potential forms. If 3I Atlas loses velocity during its close approach to Jupiter, that lost kinetic energy goes somewhere, either into Jupiter's orbital motion or into some internal process inside the object itself. A subtle heating, a stress, a change we can't see from afar. The trajectory doesn't become circular, it becomes less hyperbolic. The curve bends more sharply. What would astronomers notice? Probably nothing dramatic. Positions would still match predictions within error bars. Velocities would stay reasonable. The object would still be labeled unbound. But the margin of certainty would shrink, and the doubt would live in the decimals. The excess velocity might drop from, say, 20 kilometers per second to 18 kilometers per second. Still hyperbolic, still escaping, just less comfortably so. And then time passes. The object moves farther from the sun. Solar gravity weakens, but non-gravitational forces can continue. Solar pressure fades with distance, but outgassing might not. If the object carries volatiles that sublimate across a wide temperature range, the path keeps adjusting, the curve keeps tightening, and at some point, if enough energy is lost, hyperbolic becomes parabolic. Zero excess velocity balanced on the boundary between escape and capture. From parabolic to elliptical is a whisper. One more small force, one more tiny change, and the object becomes bound, not to a neat circular orbit, not to a stable, predictable path, but to an eccentric, chaotic loop that could swing it back into the inner solar system someday, in decades, or in centuries. The timeline depends on how much energy was lost and where in the orbit that loss happened. No such reversal has been confirmed for 3I Atlas. For now, it remains only a possibility written in the margins of the sky. The official solution is still hyperbolic. The excess velocity, smaller than the first drafts, but still above zero. So the classification remains leaving forever. But that word still carries weight. It suggests ongoing verification, repeated measurements, constant recalculation. It means astronomers keep watching, checking and rechecking, making sure the hyperbolic label is still earned. And if they stop watching, if 3E Atlas slides too far out to track with confidence, if telescope time is pulled toward other targets, other priorities, other crises, then the last confirmed trajectory becomes the assumed trajectory. Hyperbolic, because it was hyperbolic the last time we looked. Leaving, because it was leaving when the eyes turned away. Until decades from now, someone points a telescope at the right patch of dark and finds something incoming that looks unsettlingly familiar. Hyperbolic until it isn't. It sounds like a contradiction, but in orbital mechanics it's really a description of measurement limits and how certainty erodes, grain by grain, over time. Part 4, the slingshot. Nobody modeled for it, because gravity assists are supposed to be simple. You treat the object like a point mass with a known velocity. You treat the planet like a much larger point mass with a well-mapped field. You run the path through that field using equations Newton wrote 3 centuries ago. Clean, calm, and elegant on paper. The object arrives on one line, gets bent by gravity, and leaves on another line. No engines, no thrust, no complications, just predictable physics. Except comets aren't point masses. They're dirty snowballs, lopsided, porous, changing, surfaces that respond to heating by venting gas and shedding dust. Even some asteroids misbehave if they hide ice or volatile pockets. And interstellar objects are the rarest category of all. We've observed exactly 3. 3, a sample size that wouldn't pass peer review in almost any other science. So we assume they follow the same rules as our local comets. We assume outgassing, if it happens, follows familiar patterns. We assume rotation averages away the worst asymmetries. We assume, a lot, non-gravitational forces are real, documented, measurable. Halley's Comet returns every 76 years, yet its timing drifts from pure gravity, because outgassing creates thrust that can speed it up or slow it down, depending on orientation, like a faint, invisible breath. Comet Encke shifts by roughly a couple of hours per orbit for similar reasons. These aren't rounding errors. These are forces strong enough to move arrival times by hours, even days, in a single sweep through the inner solar system. Now scale that up to an interstellar body moving at 60 plus km/s. Jupiter's influence plays out over days or weeks, depending on how close the pass really is. During that window, if 3 Atlas is venting, the direction and the magnitude matter enormously. If it vents in a balanced, predictable way, some effects can cancel. But if it vents asymmetrically, if one hemisphere is more active, you get a net force fractions of a millimeter per second squared. Tiny, persistent, and patient. Here's where the speculation turns uneasy. A powered slingshot isn't only about outgassing, it's about timing and orientation. If the thrust vector happens to align with the exact bend needed to redirect the exit path toward the inner solar system, then forces compound. Gravity curves the track, and thrust nudges it further. Together, they can produce a change larger than either would alone. This isn't fantasy, it's applied mechanics. Every deep space mission that uses a gravity assist tries to add a small push near periapsis, because that's where a tiny delta V buys the biggest change in the final arc. Cassini fired its main engine during the Jupiter flyby to fine-tune its route to Saturn. New Horizons did something similar on its way outward. That's standard practice, because the math amplifies small burns near a giant. But spacecraft are controlled. Engineers know the craft's mass, its attitude, its thrust. They command burns at precisely calculated moments. 3i Atlas has no engineers, no programming. If it produces thrust, it's because physics triggers it. Solar heating, volatile sublimation, pressure release from within. Those processes don't care about optimal timing. They happen when conditions flip the switch. Except, what if the orientation isn't random? What if rotation, tidal effects, or sheer cosmic coincidence places it in a posture that produces thrust at exactly the worst moment, or the best moment, depending on your perspective? The moment Jupiter's gravity is bending the path most sharply, when even a slight extra nudge can send the object onto a new exit corridor. To be absolutely clear, there's no evidence of artificial propulsion, no rockets, No claim of intelligent control. But natural processes can generate thrust. Comets do it every day. And if a comet-like interstellar body vents during closest approach to Jupiter, physics doesn't care whether the timing was deliberate or accidental. The outcome is the outcome. Models simplify because they must. No one can simulate every grain of dust, every microcrack, every temperature gradient, every pressure pocket inside a rotating, venting nucleus. So we approximate, we assume. We model the object as solid, non-venting, sometimes even conveniently, average. Then we calculate what Jupiter's gravity should do. If the real object violates those assumptions, predictions drift. And the more extreme the encounter, the more the drift matters. Orientation could matter in another way. If 3 Atlas is elongated cigar-like, as some argued for Oumuamua, then the tidal gradient near Jupiter pulls unevenly along its length. A long body passing close to a massive planet feels differential gravity, harder on the near end than the far end, like a slow stretch in the dark. If it's tumbling, those forces can average out. But if rotation is slow, or partly locked, if one end keeps facing Jupiter during approach, the tidal coupling becomes asymmetric. That asymmetry can torque the object, alter its spin state, and that, in turn, changes how outgassing produces thrust. This is the kind of complexity that makes scientists uneasy, but curious. Uneasy because it adds variables, unknowns, ways for forecasts to fail. Curious because nature doesn't respect our simplifications. Nature follows the physics, even when the physics becomes messy. So when someone says 3 Atlas is on a simple gravity assist trajectory, what they really mean is, we modeled it simply, and it mostly fits so far. But models are only as good as their assumptions. If any assumption is wrong, venting, odd orientation, tidal response, then the simple story becomes a comforting fiction. And the real trajectory may be something we won't fully understand until it's too late for understanding to matter. Part 5. The silence problem. When an asteroid is discovered, especially one that might threaten Earth, data moves fast. Observatories track it, orbits update daily, NASA's CNEOS posts refined predictions. Amateur astronomers contribute their own measurements. The object gets a designation, a risk assessment, a public consensus. Within days or weeks, the community usually converges on an answer. If it's not dangerous, the world exhales and moves on. Interstellar objects begin the same way. Discovery sparks excitement. Telescopes swing toward it. Data pours in. Orbital elements tighten. The object is labeled interstellar by its velocity and geometry. Papers appear, press releases echo. And then, gradually, attention fades. Not because it stopped being interesting, because it's far, fast, expensive to track, and time is finite. Observing schedules are crowded. Other targets demand priority. This is normal astronomy. You can't follow every object forever. You gather enough to characterize the path, confirm no immediate threat, and move on. For most bodies, that's enough. For interstellar visitors, it should be enough, because they're supposed to pass through and vanish into deep time. Except, the absence of updates can feel louder than the updates themselves. When months pass without new refinements, without fresh public notes, silence fills the space where certainty used to sit. And human minds are experts at filling silence with stories, usually the wrong ones. Online speculation thrives in gaps. Forums and feeds turn into echo chambers for anxiety. If it were safe, people reason, wouldn't scientists keep saying so? If it were predictable, wouldn't we see constant updates? A lack of information becomes information. Silence becomes evidence of something hidden, something dangerous, something unspeakable. It's unfair to scientists who are often just busy and bound by schedules. Major telescope time is allocated months ahead. Proposals are reviewed. Priorities are locked. An object already characterized usually drops down the list unless something changes. And if nothing has changed, or the changes are small inside expected margins, there's no reason to issue updates. No news can genuinely mean good news. But institutional caution can look like concealment. When statements hedge with phrases like, current observations suggest, and within projected parameters, the hedging gets misread as doubt. When updates grow less frequent, silence gets interpreted as evasion. And when someone notices the last detailed trajectory solution is now months old, that outdated certainty becomes fuel for conspiracy. Interstellar objects also fall outside some standard pipelines. The Minor Planet Center tracks solar system bodies, cleanly categorized. The IAU names comets and asteroids, but interstellar visitors don't fit neatly into the old drawers. They aren't minor planets. They aren't quite comets. Even when they act comet-like, they're exceptional, which means exceptional handling, and exceptional things sometimes slip through bureaucratic seams. The result can be a strange informational void. Everyone agrees 3 Atlas is interesting. Everyone agrees it should be monitored. But no single institution owns the duty of constant public updates. NASA observes, ESA observes. Amateur networks track when they can, but coordinated, ongoing communication is hard, especially when the object isn't an immediate threat, and priorities pull in different directions. Then there's uncertainty itself. Science speaks in error bars, confidence intervals, probability ranges. Public communication wants certainty. Headlines want yes or no. Readers want one simple verdict: dangerous or not. And the honest answer is usually, probably not, but we can't be perfectly sure. That answer satisfies no one. To skeptics, it sounds like evasion. To optimists, it sounds like alarm. So scientists err on caution. They state what the models show today. They avoid vivid speculation about low probability edges. They don't want to cause panic, and they don't want to look foolish if speculation collapses under new data. In that sense, silence can be protective, an attempt not to manufacture fear where none exists. But silence is a vacuum, and vacuums get filled. If official sources won't discuss unlikely scenarios, unofficial voices will. If scientists won't imagine what happens if models are wrong, the internet will. And because unofficial speculation isn't bound by peer review, it drifts toward drama. Worst case gets amplified. Possibility becomes probability. Probability becomes certainty. None of this means 3 Atlas is actually dangerous. It doesn't mean the models are wrong. It doesn't mean anyone is hiding the truth. It means human psychology hates uncertainty and will paint pictures in the dark when the room goes quiet. Once anxiety takes root, it's hard to pull out cleanly. The silence isn't evidence, but it isn't nothing either. It's a gap, a pause, a place where fresh certainty isn't being replenished. And as 3 Atlas continues outward, that gap widens. The last confirmed solution grows older. Confidence intervals soften. Numbers become fuzzier at the edges. The question shifts from, where is it now, to, where was it when we last checked? And if it returns, if decades from now a new object is detected on an Earth crossing line, and someone runs the orbit backward and finds it matches 3 Atlas exactly, then today's silence will sound different in hindsight. Not like caution, but like a warning no one wanted to speak. Part 6. Non-gravitational forces too small or misread. Outgassing pushes comets. That's the simple version. Sunlight warms the surface. Ice sublimates into gas. Gas escapes. Momentum conservation pushes the comet the other way. It's rocket propulsion at microscopic scale. Gentle. Continuous. For most comets, it's smaller than gravity. Measurable but not dominant. Except small forces accumulate. Over enough time, tiny pushes become real changes. But the simple version hides one crucial word: direction. Not all outgassing is equal. If a comet vents uniformly, forces cancel out. Thrust from one side balances thrust from the other. Net effect, nearly zero. But comets don't vent uniformly. Solar heating creates day-night contrast. The sunlit face becomes active. The dark face stays quiet. That creates asymmetric thrust, usually pointing away from the sun. And even that is an oversimplification. Nuclei rotate. As they spin, different regions face the light. If rotation is fast, the asymmetry can average out. But if rotation is slow, or locked, or dominated by vents that don't follow sunlight, then thrust can stay coherent in one direction. That's when outgassing stops being a minor perturbation and starts becoming a real orbital actor. For 3I Atlas, we don't truly know the rotation state. We know it's interstellar, formed around another star under unknown conditions. We know it's fast ejected violently, or accelerated by encounters we never saw. We know it shows comet-like signals, meaning volatiles may be present. But rotation, composition, internal structure are educated guesses. And the guesses matter. Chaotic tumbling could average thrust away. Slow rotation could make thrust persistent. A spin axis aligned with motion, or perpendicular, or tilted just so, changes the thrust vector and the fate of the path. And that thrust vector decides whether outgassing speeds it up, slows it down, or nudges it sideways. Now consider Jupiter. Solar heating is weaker that far out, but gravitational stress can crack surfaces, exposing fresh ice. Tidal forces can flex an object, generating heat through internal friction. If 3 Atlas passes close enough, the encounter itself could trigger venting. Not sunlight-driven venting, gravity-driven venting. Speculative, but grounded in real phenomena. Io is the most volcanically active world in the solar system, because Jupiter needs it with tidal forces. Enceladus vents water vapor, because tidal flexing keeps cracks alive. Tidal heating is real, measurable, repeatable. So now you have 2 possible thrust sources: solar-driven outgassing that fades with distance, and tidal-driven outgassing that spikes near closest approach and then quiets. Both are non-gravitational. Both are small next to Jupiter's pull, but both can accumulate, and accumulation is where trajectories change. Now the size question becomes critical. How small is too small to matter? Engineers measure thrust in newtons. Astronomers infer comet thrust by orbital deviations and back calculation. Often the force is tiny, less than you'd use to lift a glass of water, but applied steadily over weeks or months. Even a fraction of a newton can shift an orbit by thousands of kilometers. The problem is measurement. We don't measure thrust directly. We can't. There's no accelerometer on 3i Atlas, no telemetry, no onboard sensors. We watch its position. We compare to predictions. We attribute mismatch to non-gravitational forces, but that attribution carries assumptions, and assumptions can be wrong. If it brightens, we assume outgassing. If it speeds up slightly, we assume thrust along the path. If it drifts sideways, we assume a lopsided vent. But what if brightening is just rotation, a reflective face turning toward us like a mirror in the dark? What if velocity shifts are measurement artifacts? What if the deflection comes from a force we haven't named yet? Residuals tell us something is happening, not what. And then there's coherence. For outgassing to meaningfully reshape a path, thrust must be coherent, pushing in roughly the same direction long enough to matter. Random venting creates noise. Coherent venting creates a signal. And signals are what our instruments can trace across time. Most comets get coherence from rotation. They spin, but their spin axis stays roughly fixed. So jets keep pointing in consistent directions relative to the orbit. That's why tiny forces can add up into real changes. And why, in the deep quiet near Jupiter, even a whisper of thrust can matter. The residuals tell us we're seeing a push, but they don't tell us the hand behind it. Coherence is the difference between a harmless shimmer and a steady, patient steering. And when you're moving at interstellar speed, a steady millimeter becomes a mile, then a world. Coherent venting, persistent and directional, produces a measurable signal. Noise gets swallowed by uncertainty, but signal survives. And if 3 Atlas has a stable axis, a consistent vent, a repeating pattern, then even nature alone could write a trajectory far stranger than our simplest models ever dared to predict. Over time, those jets behave like tiny engines, firing again and again in nearly the same direction. For 3i Atlas, that kind of repetition adds up. If the spin is steady and the venting favors one side, the push can quietly accumulate. Small forces become meaningful forces. But we don't yet know the spin is steady. We don't yet know the venting is truly asymmetric, or whether it flickers and cancels itself out. We're reading its behavior through a fog of indirect measurements, then trying to make it fit models built for familiar, local objects. If 3 Atlas plays by slightly different rules, if interstellar bodies carry quirks we haven't catalogued, then the models don't fail loudly. They fail softly. Predictions drift, and that drift gets filed away as noise until it grows too large to ignore. So are the non-gravitational forces on 3 Atlas too small to matter? Or are they being misread, misattributed, misunderstood? The honest answer is simple. We don't know. The measured accelerations are tiny, in millimeters per second squared numbers, so small they sound like nothing at all when spoken aloud. But tiny is not the same as irrelevant. In orbital mechanics, especially at high speed, near a massive world, small pushes delivered at the right moment can bend a path enough to separate a one-time flyby from a slow, eventual return. Intriguing, not alarming, that's the official framing. Interesting forces, worth studying, but not threatening, assuming the data are right, assuming the equations are complete, assuming nothing subtle has slipped past us. Part 7. The orientation anomaly. Spin matters. It sounds like a simple sentence, but it opens a door into a hidden universe of complexity, like finding a second sky inside the first. An object tumbling through space doesn't only glide along an orbit, it also turns. And that turning influences everything. How it flashes in sunlight, how it breathes out gas, how it answers tidal gradients, how radiation pressure nudges it like a faint, invisible wind. Change the spin state, and you change the story. For most asteroids and comets, that story is messy, rotation is chaotic. Collisions long ago concede random angular momentum. Close encounters can tilt a spin axis. Outgassing can add torque. The result is often a complicated tumble that never settles into a clean, stable rhythm. Measuring it is hard, because we're trying to read a whisper of motion from a speck of light. You watch the brightness rise and fall as different faces catch the sun, and you try to hear a steady beat inside the flicker. You fit a model to the light curve and extract a period. Sometimes you get lucky. One axis, one clean cycle, a simple clock. Often you don't. With interstellar objects, it's harder still. They're dim, they're distant, they sweep across the sky fast. The observing window is brief, and every night lost is a chapter you can't reread. By the time you've gathered enough data to sketch the light curve, the visitor is already receding, fading into the dark. Oumuamua was the perfect example. Weeks of observations, enough to reveal it was elongated and tumbling, yet not enough to fully pin down its spin state or explain every irregular beat. And so the questions linger for 3i Atlas. Our rotation constraints are incomplete. Early hints suggested a period of several hours, comfortably comet-like, but the light curve is noisy, stubbornly irregular. Some analyses point to precession, where the spin axis wobbles like a slowing top, tracing a small circle in space as it turns. Others suggest complex rotation tumbling around multiple axes at once. Without longer, cleaner observations, we can't know for certain. But that's why spin keeps returning, in every serious discussion, gravitational coupling. When an elongated body swings past something massive like Jupiter, tides interact with shape and with rotation, pulling unevenly across the body's length. If the long axis points toward Jupiter near closest approach, the gravity gradient tries to stretch it, like a hand pulling gently on both ends. If the object rotates so that many orientations face Jupiter in quick succession, those tidal pulls average out. But if the rotation is synchronized with the motion, if it becomes tidally locked, even briefly the coupling can persist. Tidal locking is common in our solar system, a quiet handshake between gravity and time, and a reminder that motion can be negotiated into habit. Our moon is tidally locked to Earth, always offering the same face. Many moons of Jupiter and Saturn do the same. The mechanism is friction. Tidal flexing makes heat. Heat dissipates rotational energy, and rotation gradually slows until it matches the orbital rhythm. For a comet passing Jupiter only once, there isn't time for full locking, but temporary coupling is not out of the question. Even a short-lived grip can matter if it happens at the moment the trajectory is being bent most strongly. And if coupling happens during close approach, it can alter the trajectory. An elongated object aligned with Jupiter's gradient experiences different torques than a tumbling one. Energy transfer shifts, exit direction shifts. Even the final speed can change, slightly, but slightly is where the future hides, because distance turns fractions into fate. Because we don't know the exact spin state, we can't fully model the encounter. This isn't conspiracy, it isn't hidden information. It's the ordinary, frustrating problem of insufficient data. Spin measurements need long baselines and multiple viewing geometries, different angles, different nights, enough time for the pattern to repeat cleanly. For a fast, faint object like 3i Atlas, you don't get that luxury. You get one narrow angle during the brief window when it's bright enough to follow. If that angle doesn't reveal the spin clearly, you're left with inference. Then comes the question of statistical rarity versus impossibility. Some researchers note that if 3i Atlas were oriented just so during its Jupiter flyby long axis, perpendicular to its velocity, rotation axis aligned with Jupiter's gradient, the resulting deflection would be maximized. That's an exacting configuration. Multiple parameters have to line up. What are the odds? Hard to say. If orientation is truly random, the odds are small, one special pose among countless possibilities. But if the spin state has been shaped by earlier encounters, by slow thermal cycling, or by repeated outgassing torques, the distribution might not be random at all. It might have preferences that we haven't learned to recognize. And even low odds are not zero. Rare things happen. That's what rare means. The trouble is that rarity feels suspicious to pattern-hungry minds. When several unlikely steps arrive in sequence, we start drawing lines between them. 3 Atlas approaches Jupiter fast. It passes close enough for a meaningful gravitational exchange. Its spin state, still poorly constrained, happens to favor maximum deflection. Non-gravitational forces appear at the least convenient moment, and the combined effect nudges the exit path back toward the inner solar system. Each step alone is plausible. Together, they can feel orchestrated. But nature doesn't orchestrate. Nature is indifferent. If the configuration is possible and the physics allows it, then it can happen without motive, just the quiet lottery of angles and time. The universe is vast. Time is long. Rare events are happening somewhere, all the time. The question is whether we're watching one now. Observational limits pile uncertainty on uncertainty. Ground-based telescopes struggle to resolve details on an object hundreds of millions of kilometers away. Space telescopes see better, but their schedules are tight. You get snapshots, not a continuous film, and from snapshots, you must infer motion, rotation, surface behavior, and invisible venting, the faint exhale that can't be photographed directly. It's like trying to diagnose an engine from a few distant photographs. You can make educated guesses, but you are always missing something, and the missing part is where speculation lives. If we knew the spin precisely, we could model the Jupiter encounter with confidence. If we knew the surface chemistry, we could forecast outgassing patterns with more than hope. If we knew the internal structure, we could estimate tidal response. But we don't. We infer. We approximate. We borrow assumptions from local comets that may not apply. So when someone says the orientation of 3 Atlas is anomalous, what they really mean is that the data refuse to sit neatly inside the simplest models. There are irregularities, unexplained light curve features, persistent residuals in the trajectory. Could these be artifacts of measurement? Yes. Could they be signs of unusual rotation? Also yes. Could they hint at something we haven't even named yet? That too. Coincidence versus intent matters to our emotions but not to physics. Physics doesn't care why an object is oriented a certain way. It only cares that it is. If a given orientation produces a given outcome, the outcome follows whether the pose was chance or choice. Humans crave meaning. Physics obeys equations. And those equations feel unsettling when the pattern keeps pointing in one direction. Multiple uncertain factors combining into a gentle drift away from clean escape and toward a possible return maybe, if the models are missing something. Part 8. Could Jupiter be used deliberately? Let's be clear from the beginning. This section is speculative, a thought experiment. There is no evidence that 3 Atlas is under intelligent control. There is no indication its path is anything other than the result of gravity plus small natural forces. But thought experiments have a purpose. They test boundaries, sharpen questions, and make us look at scenarios we'd otherwise dismiss too quickly. So, let's look. Jupiter is the solar system's largest energy reservoir after the Sun, not in heat or light, but in gravitational potential. If you want to change course in space, you either bring fuel and burn it, or you borrow a gravity well and let physics do the heavy lifting. Fuel is costly. You must launch it, carry it, spend it efficiently. Gravity wells are free. You only have to arrive on the right line. Mission designers at NASA and ESA know this instinctively. Nearly every deep space probe in the last 40 years has leaned on gravity assists to reach its destination. Voyager, Galileo, Cassini, New Horizons, Juno, each one touching Jupiter's power at some point. Jupiter's mass is so immense that a close flyby can add or subtract kilometers per second without burning a drop of fuel. It's the ultimate force multiplier. Here's the key. The closer you pass, the more energy you can trade. Voyager 1 skimmed within roughly 350,000 kilometers of the cloud tops, and Jupiter bent its path by tens of degrees, boosting its speed by more than 10 kilometers per second. Had Voyager passed closer, the effect would have grown. Energy transfer scales with proximity, and the curve is unforgiving. Close passes change everything. Now imagine an object built to maximize that exchange, not a helpless projectile, but something capable of adjusting approach angle, timing, even orientation with tiny, patient corrections. You wouldn't need much thrust. A few meters per second of delta V applied at the right moment could shift periapsis by hundreds of kilometers. Those hundreds of kilometers change the deflection angle, and that change cascades into a very different exit direction over time, over distance, by astronomical amounts. This is why gravity assists feel like magic, even though they are only mathematics. A small burn near periapsis gets amplified by Jupiter into a large change downstream. Engineers call it the O-berth effect. Thrust applied deep in a gravity well, while you're moving fast, buys you more orbital energy than the same thrust applied elsewhere. not magic conservation of energy, paired with the non-linear geometry of orbits. So, could an object use Jupiter deliberately? Could something with minimal propulsion execute a powered slingshot to redirect itself? From pure physics, yes. The equations allow it. You'd need precise timing, accurate ephemerides, and the ability to apply thrust at chosen moments during the encounter brief, taps that matter more than long burns far away, and the energy requirements can be surprisingly low. A few hundred meters per second, applied strategically, could turn a flyby into a wide U-turn, not by stopping the object, but by pivoting its momentum around Jupiter's immense curve. Compare that to ordinary interplanetary travel. Earth to Mars costs kilometers per second. The outer planets cost more. But if you're already arriving at interstellar speed and only want to steer, you're not building velocity from zero, you're nudging a trajectory that already carries enormous energy. You're redistributing what's there, and Jupiter is uniquely suited for it. Saturn is strong, but farther out. Uranus and Neptune are farther still. Earth and Venus are small. Mars is smaller. Jupiter sits in the perfect place, massive enough to matter, close enough to reach. If you were planning an interstellar tour and wanted local gravity to help you pivot, Jupiter would be the obvious hinge. But here's the uneasy point. A maneuver like that requires information. You must know where Jupiter is. You must time the approach. You must understand orbital mechanics in a way that implies intelligence or an autonomous system sophisticated enough to imitate it. Natural rocks don't plan. They don't calculate. They don't aim for a particular periapsis the way a navigator would. They don't time outgassing with encounters, unless the timing is coincidence. Unless 3I Atlas is venting naturally solar heating, internal fractures, slow sublimation from a sheltered pocket, and it just happens to vent during the most dynamically important moments of its path. Unlikely, but not impossible. We've already seen how spin can shape the direction of venting. If the rotation is even loosely synchronized, outgassing can become semi-coherent, not planned, just fortunate. Or, for the sake of the thought experiment, what if the object isn't natural at all? What if it's a probe built to survey systems by riding gravity wells like currents? Peak speculation, yes, but useful to examine. A probe wouldn't have to be large. It could be mostly inert, with minimal active systems. It could use stored volatiles, heated by sunlight, as a gentle reaction mass propulsion that looks like outgassing. It could time tiny nudges by sensing gravitational gradients and adjusting accordingly. All of that is compatible with known physics, even if it's beyond our current engineering. And if such a probe existed, Jupiter would be its ideal tool. Arrive from interstellar space, let the sun shave off a little speed, then let Jupiter redirect you without spending much fuel. The inner solar system becomes accessible at low energetic cost, and to an outside observer, it could look exactly like a natural deflection plus minor non-gravitational forces. Only deep analysis might reveal that the forces were suspiciously well-timed. None of this is evidence. None of this is a claim. It's the kind of quiet speculation scientists might entertain over coffee and discard in public, because extraordinary claims demand extraordinary evidence, and we don't have it. Still, the physics is real. The possibility exists, and that possibility is unsettling because it shifts the question from could nature do this to could intelligence do this? The answer to both is yes. Nature can produce a lucky alignment of spin, venting, and geometry that yields a Jupiter-assisted U-turn. Intelligence could plan one. Distinguishing between them from sparse observations is nearly impossible. You would want active guidance, signatures, unmistakable propulsion traces, or communications. So far, we have none. So why talk about it at all? Because it clarifies what we're afraid of. Are we afraid that a natural object, by sheer bad luck, ends up on a dangerous path? Or are we afraid that it isn't natural? The distinction matters. Natural objects are predictable even when our predictions are uncertain. Artificial objects are not. They can change course. They can respond. They can surprise. But there's a third option. Maybe intent doesn't matter. If an object is coming toward Earth, whether it arrived by accident or design, is philosophically dramatic, but practically, the response is the same. Observe, calculate, prepare. A kinetic impact at 60 kilometers per second releases the same energy whether the body is comet or probe. Yet intent matters in one operational sense. If something can steer, prediction becomes harder. You can't model what can choose. And if intelligence sits behind the trajectory, we're no longer only doing celestial mechanics, we're confronting strategy. The problem shifts from astrophysics into territory we are not prepared to navigate. Part 9. If it comes back, miss, flyby, or impact. Let's imagine purely hypothetically that the worst fears prove justified. The models are wrong. The path has changed. 3. Atlas isn't leaving forever. It returns decades from now, or centuries from now, but it returns. What happens next depends on the specifics of that return, and those specifics range from harmless to catastrophic. First, the miss. Most return trajectories, even into the inner solar system, do not end in impact. Space is huge. Earth is small. Earth's orbital plane is a thin, delicate disk. A returning visitor must intersect that disk at the exact moment Earth is there, an absurdly narrow appointment. Be off by hours and Earth is hundreds of thousands of kilometers away. Be off by days and it's millions. So the most likely scenario is simple. 3. Atlas returns, passes through, and misses completely. Maybe it glides past Mars. Maybe it meets Jupiter again and gets redirected. Maybe it finally departs for good. Return does not automatically mean danger. It means only that it's back in our neighborhood, and even without impact, close encounters matter. A flyby within a few million kilometers would be scientifically priceless. Telescopes would get a second chance closer, clearer to study the visitor's shape, spin, and breath. Spectroscopy could tease out surface chemistry. Radar could constrain rotation and structure. We could learn more in a few weeks than we learned in the entire first pass. And if something truly unusual is going on, we'd finally have time to examine it properly. From a safety perspective, a close flyby is also a warning shot. If 3 Atlas passed at roughly lunar distance about 400,000 kilometers, that would be frightening, but not immediately fatal. It would prove the geometry can bring it close. It would suggest future encounters could be closer still. It would give planetary defense teams a real target for planning, turning distant dread into concrete preparation. Now the darker branch. What if the return doesn't miss? What if the geometry aligns, the timing coincides, and 3 Atlas intersects Earth's orbit precisely when Earth is there? Then you have an impact. And at 60 plus km, the energy is almost beyond intuition. Kinetic energy scales with the square of velocity. At 60 kilometers per second, each kilogram carries 36 times the kinetic energy of that same kilogram at 10 kilometers per second. Most threatening asteroids arrive at 15 to 25 kilometers per second and are already devastating. Chicxulub, the impact tied to the dinosaur's extinction, arrived around 20 kilometers per second. That was enough to rewrite Earth, to change climates and endings and beginnings. Scale that to 60 kilometers per second. A body the size of a football field, perhaps 200 meters, could release energy in the thousands of megatons. Not a planet killer, but a regional catastrophe. In the ocean, tsunamis could shred coastlines thousands of kilometers away. On land, the blast zone could span hundreds of kilometers. The shockwave would race around the globe. Dust and debris injected into the stratosphere could dim sunlight for years, and there would be little we could do to stop it. That is the hard truth planetary defense experts rarely say out loud. Our current defenses are built for slower intruders, the kind that drift like slow sparks across the survey images. DART, the double asteroid redirection test, proved we can tweak an asteroid's orbit by slamming into it at roughly 6 kilometers per second. That's remarkable. But DART also depended on something precious: time to reach the target, align the intercept, and commit to the impact. For a slow-moving rock spotted years ahead, with long lead time and clean tracking, that's realistic. For 3 Atlas, racing at nearly 10 times that speed and possibly offering far less warning, DART becomes irrelevant. You can't reliably intercept something moving that fast with today's hardware. The closure rate is brutal, launch windows tighten to a sliver, and even a successful hit wouldn't transfer enough momentum to shift its path by a meaningful margin. At those velocities, the encounter is over almost as soon as it begins, leaving no room for last-second corrections. Deflection is, at its core, a velocity problem. To push an object off an Earth-crossing line, you need to change its speed by at least tens of meters per second, depending on how much warning you have. Less time means more delta V, because you're not just moving the object, you're moving where it will be when Earth arrives. With a decade of notice, centimeters per second can be enough. With only months, you're talking meters per second, a shove instead of a whisper. With only weeks, you're suddenly in the realm of kilometers per second of required delta V numbers that belong to rockets, not gentle nudges. And 3 Atlas is not small. Estimates range from tens of thousands to hundreds of thousands of tons. Shifting that much mass demands enormous energy. A nuclear device standoff bursting near the surface might help if you could arrive in time, but its effectiveness depends on distance, surface physics, spin state, and whether enough material is ablated in one direction to create real thrust. Not impossible, just far from guaranteed. So what about an atmospheric graze? If 3I Atlas comes in shallow, it could skim the upper atmosphere without a full ground strike. Drag would heat it, maybe fracture it, yet the core mass could survive and continue back into space, leaving the planet shaken by airburst effects instead of a crater. We see shallow entries with meteors all the time. Objects dip in, slow, flare, and skip away, turning briefly into a line of fire and then vanishing. But at 60 kilometers per second, a graze becomes an atmospheric catastrophe. The object would crush the air ahead into a bow shock of superheated plasma, dumping energy into the sky like a colossal explosion, even without touching the ground. The atmosphere itself becomes the target, and the shock becomes the weapon. Chelyabinsk in 2013 entered at about 19 kilometers per second and released energy on the order of 400–500 kilotons. 3I Atlas, moving roughly 3 times faster, would be dramatically worse because velocity compounds violence. Then comes the warning time question. How much notice would we truly have? If 3I Atlas settles into a predictable elliptical return after Jupiter, we could track it for years, maybe decades, before any close approach. That's the best case, the calm, orderly timeline. But if its orbit is chaotic, if repeated planetary flybys keep perturbing it, confidence might not arrive until months before impact, and months is not enough to mount a meaningful defense. Our detection systems are optimized for objects already near Earth, pan-stars, the Catalina Sky Survey, and similar wide-field patrols. They scan the sky over and over, hunting for motion. They're good at spotting asteroids months to years before a potential strike, but something inbound from the outer solar system at extreme speed is harder. It stays faint until it's close, and by the time it brightens enough for tight tracking, it's already coming in, already compressing the calendar into a few nervous pages. The nightmare, then, is simple. 3I Atlas returns. We don't notice until it's only a few months out. Orbital fits converge on an Earth impact corridor. We have no credible way to deflect it. Evacuation becomes nearly meaningless because we won't know the precise strike point until days before. All we can do is watch, wait, and hope we've misunderstood the math, or that the uncertainties tilt in our favor. No impact trajectory is currently predicted. I'll say it again. No impact trajectory is currently predicted. Everything here is hypothetical. But hypotheticals do emotional work. They make us face what we prefer not to picture. Because if the models are wrong, if assumptions fail, if 3I Atlas really does return, we need to understand the stakes before the moment arrives, not after, while there's still space in our minds to plan. Part 10. Planetary Defense Built for the Wrong Enemy. DART worked. On the 26th of September 2022, NASA's DART spacecraft deliberately struck Dimorphos, the small moon of the asteroid Didymos. The collision shortened Dimorphos's orbital period by about 33 minutes. Mission success proof, in the quiet language of numbers, measured not in spectacle, but in a shifted clock. We demonstrated that an asteroid can be deflected if we see it coming and have time to prepare. But DART was designed for a specific threat profile. A small body, a few hundred meters across, found years or decades in advance, moving at typical near-Earth speeds of 15–25 kilometers per second. Under those conditions, a kinetic impactor is beautifully effective because the orbit has time to drift apart from its old future. You don't have to destroy the target, you only need to nudge it. A few centimeters per second, applied years before a predicted encounter, can shift the timing enough to turn a collision into a clean miss. Earth arrives, and the asteroid isn't there anymore. But those conditions are narrow, change the parameters, and the method starts to unravel. Make the object faster, and the impulse becomes less useful for deflection. Make it larger, and you need far more energy. Shrink the warning time, and the required velocity change jumps beyond what one impactor can deliver. DART solves one well-defined problem, and it solves it elegantly. It is not a universal fix. 3I Atlas breaks nearly every assumption DART relies on. It's fast 60+ km, far beyond typical near-Earth objects. It may be massive. Even conservative estimates land in the tens of thousands of tons. And it may be less predictable, especially if non-gravitational forces are shaping the path in ways we don't fully capture. That uncertainty makes when and where hard to state with confidence. And confidence is what mission design needs. Speed dominates everything. As mentioned earlier, kinetic energy scales with velocity squared. 60 kilometers per second carries 36 times the energy per kilogram of 10 kilometers per second. But for deflection, speed creates another trap. Interception is harder. The closure rate is enormous, and the geometry becomes unforgiving. Launch windows narrow. Course corrections must be razor precise. Think of trying to hit a bullet with another bullet, possible in theory if you know exactly where and when to meet it. You place something in its path at the right moment, and the two collide. But if the target is hypersonic and its track isn't pinned down until the final moments, interception becomes almost impossible. You're trying to collide two moving objects with timing tolerances measured in fractions of a second. For 3I Atlas, the timing problem is worse because we can't launch interceptors instantly. Rockets need preparation. Orbits must be computed. Transfer trajectories must be optimized. Even a small navigation error becomes a miss measured in thousands of kilometers. Even in crisis mode, reaching a target beyond Mars can take months to years, and if the object is already in the inner solar system, there may be no time to meet it before it meets us. So what about nukes? Hollywood loves the shortcut drill: plant, detonate, done. But blowing up an asteroid doesn't erase danger, it multiplies it. Instead of one body, you get dozens or hundreds. Some pieces burn up, some still strike. Total kinetic energy is essentially unchanged. You've turned a rifle bullet into a shotgun blast, spreading catastrophe across a wider footprint. Nuclear deflection, if it works, is subtler. The goal isn't to shatter the object, but to vaporize material on one side, so the expanding plume acts like a rocket exhaust, pushing the body and changing its velocity. In principle, it can work if you can get close enough, if the surface couples well to the energy, and if you have enough warning for that small velocity change to matter. It's an argument about angles, not brute force. But 3I Atlas is so fast that even nuclear deflection becomes questionable. Shorter warning times demand larger velocity changes. The standoff distance must be tuned. Too close, and you fragment the target. Too far, and the energy washes out without producing useful thrust. And you'd still have to launch the device, rendezvous, position, and detonate within a painfully narrow window, while the object keeps eating distance at interstellar pace. Then comes the quieter problem: detection and tracking. Planetary defense assumes we see the threat early. Current surveys are strong at finding near-Earth asteroid solar system residents with recurring orbits. We've catalogued most of the large ones, the global hazards, and we're working through the mid-sized city killer range, filling in the map piece by piece. But interstellar objects are different. We've only confirmed a few, and they're dark, fast, and hard to spot until they're already close. If 3I Atlas returns on an unpredictable line, we might not detect it until it's already heading into the inner solar system. Then warning time shrinks to months, maybe weeks. That's not enough to design, build, launch, and execute an intercept mission with real odds of success. It's barely enough to evacuate, even if we knew the impact point. And because orbital uncertainty stays high, we might not know the strike location until days before. So what can we do? Honestly, very little. Our systems are tuned for known, slower threats discovered years ahead, threats that give us the courtesy of time. For something like 3I Atlas, if it truly comes back, we may be limited to observation and prediction, track as well as we can, compute impact probability, refine the trajectory as new data arrives, and prepare for consequences rather than prevent them. It's uncomfortable, but it's the honest edge of our current capability. Planetary defense is still young, still learning its own tools. DART was a first step proof that deflection can work, but it's the first step on a long road. Systems capable of handling fast, massive, uncertain objects would take decades and enormous investment, better detection networks, faster response, stronger propulsion, and the political will to fund threats that may never arrive, yet still might. And that's the political knot. Planetary defense is hard to fund when the danger is abstract. Asteroids don't respect election cycles. The risk stretches across centuries. Few leaders want to spend billions on a catastrophe that might not happen in their lifetime. So we do the minimum, track what we can, test slowly, and hope that if something truly dangerous appears, we'll have time to respond. But hope is not a strategy. If 3I Atlas is the warning shot the visitor that exposes how unprepared we are, then the real question becomes whether we learn in time or only after it's too late to matter. Part 11. The Interstellar Object Boom, 2017. Oumuamua, the first confirmed interstellar visitor ever detected, crossing our solar system, slipping through like a silent splinter between worlds. Astronomers celebrated it was historic, a messenger from another star, proof that systems trade material across the galaxy. It was odd, elongated, tumbling, accelerating in ways pure gravity didn't quite explain. But it was there. It was real. Then, 2019 brought 2I, Borisov, the second interstellar object, easier to classify and easier to recognize. Clearly cometary in spectra, with outgassing and a coma, less mysterious than Oumuamua, still extraordinary. 2 visitors in 2 years, and the floodgates seemed to crack open. Then came 3I, Atlas. So, how many more are coming? Are we seeing an influx, or simply learning to notice what was always here? Mostly the latter, because our instruments have finally become sensitive enough to catch the faintest motion. Interstellar objects have likely been passing through all along. They didn't suddenly begin in 2017. What changed was our eyesight. Better telescopes, stronger surveys, more sensitive detectors, and sharper data processing. Pan-STARRS came online in the early 2010 seconds, watching wide swaths of sky with patient regularity. The Catalina Sky Survey expanded. Atlas, the asteroid terrestrial impact last alert system, began sweeping the sky for fast, transient motion. These surveys weren't built to hunt interstellar bodies specifically. They were built to find near-Earth asteroids, the ones that could one day hit, the ones that keep our nights from being too complacent. But the method works for anything that moves, and interstellar objects move fast. Across a few nights, they shift dramatically against the background stars. Automated pipelines flag the motion, astronomers follow up, and if the orbit shows clear hyperbolic excess, it's tagged as interstellar. Motion is the signature, a blink against a fixed galaxy. There's a selection bias, though. We mostly detect the ones that pass near the Sun and near Earth, where sunlight makes them bright enough to notice. Visitors that stay beyond Jupiter are often too faint. Objects approaching from poorly covered sky directions slip through, and small, dark bodies can remain invisible until they're extremely close by, which time they're already on the way out. So the 3 confirmed detections are only the tip of the distribution. For every one we see, dozens, maybe hundreds pass unnoticed. Estimates from detection rates suggest that at any given time, there could be thousands of interstellar objects within the solar system. Most are small, most are far from the Sunday. Most never announce themselves at all. Most will never come close enough for detailed observation. But it's still a lot of traffic. Countless fragments from other systems drifting through our neighborhood, each carrying quiet clues about distant planet formation, violent ejections, and the long physics of wandering. We're only beginning to map this population because we've only just learned how to see it, and the detection rate is about to rise. The Vera C. Rubin Observatory, scheduled to begin operations soon, is expected to transform sky surveys. Fainter limits, wider coverage, faster revisits than any predecessor, a steady heartbeat of observations. Estimates suggest it could find dozens of interstellar objects per year, not because more are arriving, but because our vision is improving. More detections mean real statistics. Right now, we're trying to understand interstellar objects from 3 examples, like trying to understand Earth's ecosystem by studying 3 animals. The sample is too small. With dozens, then hundreds, we can start describing the population, typical sizes, velocities, compositions. Are most asteroid-like or comet-like? Do they arrive isotropically, or cluster along preferred approach corridors shaped by the sun's motion through the local interstellar medium? These questions matter for planetary defense. If interstellar visitors are common, routinely threading the inner solar system, then impact probability rises, not dramatically. Space is still vast, Earth still tiny, but more objects means more chances for close passes, and, eventually, more chances for an impact. And there's another implication. If interstellar bodies are abundant, stellar systems are constantly leaking material into the galaxy. Planets form, collisions and gravitational encounters eject debris. The debris wanders, some gets captured by other stars, some drifts for eons. The galaxy becomes a vast mixing reservoir, slowly blending matter over billions of years, turning every system into a contributor. That has consequences for astrobiology. If life ever arose in another system, and if a living world was shattered or sterilized, fragments could escape as interstellar objects. Microbes might survive deep inside an icy nucleus, sheltered by meters of material from radiation and cold, sleeping through long, dark voyages. Those microbes could drift for millions of years and eventually fall onto another planet, seeding life elsewhere. panspermia not just within one system, but across the Milky Way. Speculative? Yes, but no longer absurd. If interstellar objects are common, carry organics, and impacts happen over geologic time, then life could be a galactic phenomenon, not an isolated accident, but a slow-spreading ember. And every interstellar object we detect becomes a small data point in that larger story. In the short term, though, a boom in detections also means a boom in uncertainty. More objects to track, more trajectories to compute, more risks to assess. Planetary defense was designed with the assumption that threats come from solar system objects with well-mapped orbits, with histories we can reconstruct. Interstellar objects break that assumption. They appear with little warning, can be harder to model, and often vanish before we can study them deeply. And if one is ever nudged onto a return path, whether 3I Atlas or a future visitor, then we must understand these bodies not only as curiosities, but as potential hazards, because more detections also mean more unknowns that our models must learn to hold. More objects means more opportunities for something to go wrong. Part 12. AI is now designing orbits faster than humans. Trajectory prediction used to feel straightforward. Observe positions at multiple times, fit an orbit, propagate forward Kepler's laws, Newton's equations, plus a few planetary perturbations. Computers made it faster, but the concept stayed clean. Input observations, output trajectory, done. Except for objects like 3I Atlas, where non-gravitational forces matter, uncertainties are large, and the path depends on parameters we don't directly measure, the task becomes tangled. You have to fit models with many free parameters: mass, rotation, outgassing rate, surface albedo, even shape and mass distribution. And each one nudges the trajectory a little, like tiny hands on a fast-moving trajectory. Finding the parameter set that best matches the observations means searching a multi-dimensional space. Humans can do it, but it's tedious. You simulate one set, compare predicted positions to data, adjust, run again, and iterate until the fit finally converges, sometimes after hundreds of runs, sometimes after thousands. The method works, but it costs time, days, or weeks to fully characterize one tricky trajectory. And when new measurements arrive, you often begin again. Enter machine learning. In recent years, researchers have trained neural networks on vast libraries of simulated orbits, letting them learn the mapping from observations to orbital elements, then applying that learned intuition to real data as it arrives. A network can test thousands of parameter combinations in parallel, finding high-quality fits far faster than traditional loops. And it works. AI-driven predictions are now competitive with, and sometimes better than, human-built solutions for many classes of objects. The algorithms are fast, scaling cleanly to huge datasets, and they don't tire. They're also excellent at pattern recognition, catching correlations a person might miss. For surveys tracking thousands of asteroids at once, AI is becoming indispensable. But there's a cost. Black boxes. Neural networks don't explain their reasoning. They don't show their work. You feed in data, you get a prediction, and the path in between stays opaque. A human analyst can stare at an orbit, fit and feel the logic underneath it, why one parameter was favored, why a certain observation was weighted, where the uncertainty truly leaks in. An AI, by contrast, simply returns numbers. That creates a quiet verification problem. How do you know it's right? How do you audit the work? With classical methods, you rerun the math independently and compare. With AI, you either accept the output on faith or you train a second model and hope it agrees. Neither path is comforting. Then there's overfitting. A machine can learn the quirks of its training set so well that it stops generalizing. In trajectory work, that means it may excel on simulated orbits, clean, curated worlds, yet slip on real objects whose behavior falls outside the training distribution. Interstellar visitors are the perfect stress test. We have only 3 confirmed examples, so training sets lean heavily on simulations, and simulations are only as honest as the physics we feed them. If the code assumes a certain range of outgassing rates, and the real object exceeds it, the network can deliver confident predictions that are quietly, completely wrong. And because the model can't explain its reasoning, the mistake may stay invisible until the object drifts far enough from the forecast to be undeniable. Speed is not certainty. That's the key distinction. AI can generate predictions faster than humans, but faster isn't the same as truer. It's simply faster. In a domain where accuracy matters more than time, where one misprediction could mean missing an impact, warning opaque algorithms feel unsettling. Scientists know this. AI is treated as an instrument, not an oracle, and not a substitute for judgment. Outputs get cross-checked, outliers get flagged. Human eyes still return to the data, like night watchmen pacing the same corridor, listening for the smallest creak. The hope is a partnership. AI catches patterns humans overlook, and humans catch the subtle failures AI can't recognize. But as surveys track more objects and pipelines become more automated, that balance tilts. No team can manually review every trajectory forever. Eventually, we must trust the machines, and trust becomes the real pressure point. Not technical trust, the kind earned through validation, benchmarks, and careful testing, but psychological trust. The willingness to accept that a system you don't fully understand is shaping decisions tied to planetary safety. We already do this for ordinary life. Your phone's autocorrect uses AI, and you barely notice the correction as it happens. Your streaming recommendations use AI too, but predicting the paths of potentially hazardous objects is different, especially when the algorithm's output collides with human intuition. If a veteran astronomer feels the orbit is safe but the model flags risk, who do you believe? If the human is uneasy but the network says, "Fine, do you exhale?" Suddenly the question isn't only physics, it's how we decide what counts as knowledge. Authority begins to drift from expertise toward algorithms, and algorithms can't be questioned the way a person can. For 3i Atlas, AI has been used to refine trajectory predictions. The residuals, the tiny gaps between observed and predicted positions, are fed into neural networks that try to infer the non-gravitational forces at play. The networks output best fit parameters for outgassing, rotation state, surface properties, and those parameters fold back into updated trajectory models. But the results are probabilistic. The AI doesn't say, "It will be here at this second." It offers a distribution of possible positions, clouds of futures with uncertainty that swells as the years stretch on. Interpreting those clouds still demands human judgment. Is a 1% chance of Earth intersection in 50 years alarming or negligible? What about 10% in a century? The AI can't answer. It only hands you numbers. So, we're living in a transition. Powerful, not omniscient. Fast, not infallible. Helpful, not complete. And as we lean on these tools, we have to keep their limits in view. If AI declares 3 Atlas safe, and it's wrong, the consequences are severe. If it cries danger where none exists, we spend resources and burn credibility. The balance is delicate. Use the tools, trust them carefully, verify relentlessly, and remember softly, always that the map is not the territory, and reality doesn't promise to stay inside our models. Even the best forecast is a lantern, not daylight. Remember this, gently but firmly. Predictions are models, and models are simplified sketches of reality. Sometimes they miss the small, quiet details that end up mattering most. Part 13. Solar activity is complicating everything. The sun is not a constant lamp. It radiates energy, yes, but that radiation breathes and shifts solar flares, coronal mass ejections, surges in the solar wind, subtle fluctuations in the magnetic field. All of that reshapes the space environment around Earth and across the solar system, and it complicates trajectory forecasts for small objects. Solar radiation pressure is real force. Photons carry momentum, and when they strike an object, they transfer that momentum, an almost weightless push. For planets, it's negligible. For tiny things, dust grains, spacecraft with wide solar panels, it becomes meaningful. Comets and asteroids sit in the uneasy middle, and the effect depends on size, mass, and surface area. For a typical comet nucleus a few kilometers across, radiation pressure adds a faint acceleration measured in micrometers per second squared. But months become years, and that faint acceleration accumulates. Velocity shifts by meters, sometimes tens of meters per second, and the path slowly slides. Predictions that ignore radiation pressure drift, and the complication is that the sun's output isn't steady. During solar maximum, the sun is brighter, more variable, more restless. Solar flares can briefly spike radiation intensity. Coronal mass ejections can reshape the solar wind, altering how charged particles wash over objects in space. That makes radiation pressure time-dependent, not a constant term you can neatly plug in. And we are in a solar maximum era, with elevated activity as the 11-year cycle crests and ripples. More flares, more variability, more unpredictability. For something like 3e Atlas out in the outer solar system, where sunlight is already weak, this can seem trivial. But over long time spans, tiny changes in acceleration become large changes in position. Heliophysics, the study of the sun's influence across the solar system, is still maturing. We've learned a great deal from solar monitoring spacecraft, from probes that dive close to the sun, and from Earth-orbiting satellites, tracking radiation and particle flux. But predicting solar activity remains difficult. We can forecast broad seasons of higher or lower activity, yet specific events still arrive with little warning. Solar flares are famously abrupt. That becomes a problem for long-range trajectory work. If you're trying to estimate where 3I Atlas will be in 20 years, you have to account for the cumulative effect of radiation pressure across those decades, and when the driver varies unpredictably, the uncertainty must grow the further forward you project. And there's coupling. Radiation pressure interacts with outgassing. Sunlight warms a comet-like surface. Gas vents. Venting creates thrust. But that heating depends on how much sunlight arrives, which depends on solar output. More radiation means more heating, more sublimation, more thrust forces stacking quietly on top of forces. Now add spin geometry. If 3 Atlas has a rotation axis tilted away from its orbital plane, different regions heat at different times. Outgassing becomes directionally variable, sometimes nudging forward, sometimes sideways, depending on which hemisphere faces the sunday. And if solar activity fluctuates, the heating pattern flickers and shifts, making the venting less predictable still. These interactions are known, but modeling them precisely is hard. The coupling between radiation, heating, and outgassing is nonlinear. Small changes in one input can produce disproportionate changes downstream, and when the object is billions of kilometers from the sun, already difficult to observe, the uncertainties multiply. Recent research has underscored how much we still don't know. Even Jupiter-family comets, watched for decades, show persistent trajectory quirks that our current models don't fully explain. The anomalies are tiny fractions of a percent, but they're real. Something is missing. It might be solar variability. It might be complex surface physics. It might be internal structure. We don't know. And if we can't fully explain objects we've studied for years, how confident should we be about one we've watched for only months? This isn't alarmism. It's scientific humility. The universe is complicated, and our models are approximations excellent most of the time, but exposed at the edges. Interstellar objects are, by definition, edge cases. For 3I Atlas, solar activity adds another thin layer of uncertainty, another faint hand on the trajectory we can't see directly. Radiation pressure fluctuates. Outgassing responds to heating patterns we can't observe in detail. Over years or decades, the cumulative effect could shift the path by thousands, perhaps millions of kilometers. And those shifts could separate a harmless departure from a trajectory that drifts back toward Earth. So, when orbital predictions come wrapped in wide uncertainty ranges, this is part of why, not because scientists can't do the math, but because the inputs to the math are inherently uncertain. Solar activity is only one factor among many, but it's not optional to ignore, and the farther we project, the more small uncertainties stack, and the less reliable certainty becomes. The sun complicates everything, not maliciously, simply by being itself, variable, powerful, unpredictable, driving conditions across the entire solar system. For an object like 3 Atlas, that influence could be the difference between a benign curve and one that demands attention. Part 14. When small forces win. In mathematics and physics, chaos has a specific meaning. It doesn't mean randomness. It means sensitive dependence on initial conditions. Tiny differences at the start can blossom into drastically different outcomes over time. Weather is the classic example. A butterfly flaps its wings in Brazil, and weeks later, a hurricane forms in the Atlantic, not because the butterfly caused the storm, but because chaotic systems amplify small perturbations. Orbital mechanics can be chaotic too. For stable orbits, chaos barely matters. Earth goes around the sun with comforting predictability. We can calculate its position centuries ahead with high confidence, as we can for the other planets. Their orbits are regular, periodic, not chaotic. But add a third body, introduce close encounters, include non-gravitational forces, and chaos can emerge. Asteroids in certain regions show this. The Kirkwood gaps exist because objects there undergo chaotic interactions with Jupiter. Over millions of years, that chaos ejects them. Comets, especially long-period visitors from the Oort cloud, also behave chaotically because their paths bring them close to planets where gravitational perturbations dominate. For 3 Atlas, approaching Jupiter at high speed, chaos matters. A slightly different approach angle, a fractionally different velocity, and the exit trajectory can change dramatically. That sensitivity means predictions have horizons. You can't confidently say where the object will be in 1,000 years because small errors today can compound, then compound again. And it isn't only gravitational chaos. Non-gravitational forces add additional sensitivity on top of it. If outgassing produces thrust, its magnitude and direction depend on rotation state, surface properties, and solar heating, each with its own uncertainty. Stack those uncertainties, propagate them forward, and the error bars grow. Eventually, they grow so wide that the prediction stops being useful. That's a fundamental limit, not a failure of effort. Even perfect equations, paired with perfect data, still have prediction horizons in chaotic systems. Beyond that horizon, you're not forecasting, you're guessing. The physics remains deterministic, meaning that if you knew everything perfectly, you could predict perfectly. But you don't. You can't. Measurement errors, however small, erode long-term predictability. Modern physics keeps reminding us that chaos appears in unexpected places. Three-body problems once imagined solvable with enough computation can produce chaotic solutions that resist neat analytical certainty. Multi-body gravitational systems, like planetary systems, can be chaotic over long timescales even when they look stable in the short term. The implication for planetary defense is sobering. We can predict near-term threats reasonably well decades, perhaps a century. Beyond that, reliability fades. An object calculated to miss Earth by a wide margin in 200 years might still hit, simply because tiny uncertainties accumulate into large deviations. And the reverse is also true. Something flagged as hazardous might become harmless once we account for forces we initially missed. Newton's laws still work. This matters to say out loud. Chaos doesn't mean physics breaks. It means outcomes are sensitive to details. The equations remain accurate. But it's still garbage in, garbage out. If your initial measurements carry errors, chaos amplifies them. For 3I Atlas, every measurement has uncertainty, position by hundreds or thousands of kilometers, velocity by meters per second, mass as a rough estimate, spin state only loosely constrained. Each uncertainty feeds into trajectory predictions, widening the cone of possible futures, and the widening is uneven. Predictions near perihelion, where accelerations are strongest, are more sensitive than those far out. Predictions involving close planetary encounters are exponentially more sensitive than predictions through open space, which means the most critical part of 3I Atlas's story, its Jupiter flyby, is also the least predictable in the long run. This isn't comfortable. We want certainty. We want crisp statements, safe or dangerous. But chaos refuses that simplicity. It forces probabilistic thinking. Instead of "it will be at position X at time t," we say it has a distribution of possible positions centered near X, with uncertainty that expands over time, and eventually that distribution grows so broad it can contain both safe and dangerous outcomes. At that point, we're not truly predicting, we're bracketing possibilities. The only way to narrow them is more data, better observations, refined measurements, continuous tracking. But tracking has limits. Objects fade. Telescopes have finite sensitivity. At some distance, 3 Atlas becomes too faint to track accurately, and once tracking is lost, predictions freeze at the last known state. The object keeps moving, forces keep working, the trajectory keeps evolving, but we no longer see it. And when we see it again, if we see it again, it may appear far from where the frozen prediction suggested. This is the essence of when small forces win. Large forces like gravity dominate in obvious ways. Small forces like radiation pressure and outgassing work quietly, accumulating over years, shifting the path in ways that only become visible much later. In chaotic systems, those small shifts can separate safety from catastrophe. So the question becomes, are we prepared to live with uncertainty? Are we comfortable making decisions from probabilistic forecasts with error bars spanning millions of kilometers? Do we invest in monitoring objects that may be harmless, simply to be sure, or do we accept risk as inevitable, hoping most uncertainties resolve in our favor? The answer isn't singular. Institutions tend to caution. Individual researchers push boundaries. The public wants definitive reassurance, while reality stays indifferent, governed by equations that are perfectly precise, yet unpredictable beyond certain horizons. Part 15. The question we're avoiding. Let's step back, all the way back. We've talked about trajectories, models, forces, uncertainties, defenses, predictions. We've explored scenarios, weighed probabilities, tested assumptions, But beneath the analysis is a question we keep circling uncomfortable because it nudges the conversation from science toward philosophy, from facts toward fear. Are we certain 3 Atlas is leaving? Not probably leaving, not likely leaving, certain enough certainty to stop tracking, stop worrying, stop preparing, and make this entire discussion unnecessary? And the honest answer is no. We are confident, based on current models, current data, current understanding. But confidence is not certainty. Models are approximations, data has error, understanding is incomplete. There is always a gap between what we forecast and what nature chooses to do, and in that gap, surprise is live. This isn't the same as fear. Fear is emotional, often irrational, driven by worst-case imagination. What we're naming here is epistemic humility, the recognition that knowledge has edges. Science is spectacular at explaining the universe, but it's never finished. There's always another layer, another parameter unmeasured, another interaction unmodeled. For most daily purposes, that's fine. We land spacecraft on Mars without knowing every microscopic detail of orbital mechanics. We predict eclipses centuries ahead despite imperfect knowledge of the moon's motion. We're good enough, often brilliantly so, but good enough for routine operations isn't the same as good enough for existential stakes. When consequences are planetary and irreversible, good enough can feel thin, so we're left with attention. Science demands we follow the data, but incomplete data yields conclusions hedged with caveats. 3I Atlas is probably leaving. Its trajectory is most likely hyperbolic. Current models suggest no return. These are accurate statements, and they are not absolutes. And humans don't handle probability gracefully. We crave binaries, safe or dangerous, known or unknown, leaving or returning. The middle ground, partial knowledge, competing uncertainties makes us uneasy. It can look like indecision, like scientists failing to decide, but it isn't. It's honesty. It's admitting some questions don't have clean answers yet. The temptation is to pattern seek, to connect dots, to assign meaning to coincidence. 3. Atlas approaches Jupiter. The trajectory shifts a little. Non-gravitational forces appear. Rotation remains ambiguous. Individually, these facts can be mundane. Together, they can feel like a deliberate design, like a plan taking shape in the dark. But patterns can be illusory. The human mind evolved to detect patterns even when none exist, because missing a real pattern used to be more dangerous than seeing a false one. So we ask, is the pattern real, or are we draping narrative over random alignment? The difference matters, yet with limited data, distinguishing them is nearly impossible. You'd need more observations, more time, more certainty than we currently have, and by the time certainty arrives, the question may already be moot. This is the heart of it. Planetary defense often requires acting with incomplete information. Waiting for certainty can mean waiting until it's too late. Acting without certainty risks resources, credibility, and public trust on threats that may never materialize. The balance is agonizing, and institutional dynamics make it harder. Space agencies are conservative for good reason. Bold claims without evidence damage reputations. False alarms create boy who cried wolf scars. So the tendency is to wait, gather more data, refine models, raise confidence before speaking loudly. But waiting has costs too, measured in lost preparation time. For 3 Atlas, we're in the waiting phase. It's distant, faint, moving away. No immediate threat, no imminent danger. The prudent approach is to keep observing when possible, update models as data improves, and reevaluate if anything changes. Sensible and also frustrating. Because the question remains, what if the assumptions are wrong? What if Jupiter, the great amplifier of gravitational consequences, has done something we didn't anticipate? What if 3 Atlas, guided by forces natural or otherwise, isn't leaving but looping back? What if the decades and centuries ahead aren't safety buffers, but quiet countdown timers? We don't know. That's the answer. We don't know with certainty. And saying that can feel like failure, like science falling short. But it isn't failure. It's science telling the truth about its limits. The universe is under no obligation to be comprehensible on our schedules, with our tools, on demand, and Jupiter doesn't choose sides. This is the final essential truth. Jupiter is a planet, not an agent. Its gravity bends space-time according to equations that don't care about human outcomes. If those equations redirect 3 Atlas toward Earth, it isn't an attack, it's geometry. If they deflect it safely away, it isn't protection, it's geometry. The universe is indifferent. But indifference is not the same as harmlessness. A hurricane is indifferent to the city it breaks. An earthquake is indifferent to the lives it changes. Indifference and danger can coexist, and Jupiter's indifference is backed by gravitational power beyond anything we can muster, shaping trajectories across the solar system, including ours, including anything that passes close. So when we look at 3 Atlas, we're not only looking at an object, we're looking at our relationship with the cosmos. We're confronting the fact that we are small, vulnerable, and living amid forces we cannot negotiate with. Jupiter doesn't protect Earth. Jupiter amplifies consequences, whatever they are. If we're lucky, those consequences favor us. If we're not, they don't. And luck is not a plan. Luck is what we call an outcome we didn't earn, didn't predict, didn't deserve. We can do better, observe more carefully, model more accurately, prepare more thoroughly. We can reduce the role of luck by increasing the role of knowledge, though we can't erase uncertainty entirely. The universe is too intricate. Our tools are limited. Time is short. 3 Atlas might be leaving forever. It probably is, but probably is not certainly. And in the narrow space between those words, vigilance lives, where humility meets curiosity, and where science admits what it doesn't know, then keeps watching the sky anyway. In the end, Jupiter doesn't choose sides. It only amplifies consequences. And right now, we don't know which consequences it's amplifying.